It may not be obvious to you what the solvent considerations are in an SN2 type reaction, but they're there and they're relatively important. And so the take-home message is going to be always that we need to use a polar aprotic solvent for SN2 reactions. Why that is probably best illustrated with a reaction coordinate diagram. And this is a reaction coordinate diagram for a totally generic SN2 type reaction. You have a substrate bound to some leaving group, you have a nearby nucleophile. This comes at some energy level. We then eventually go on to products where now we have done the substitution reaction and the nucleophile is bound to the R group and the leaving group is floating freely. But in order to pass from one to the other, we must go through this transition state, this relatively high energy state. And at this high energy state, you have the following problem. The nucleophile is starting to make a bond to the carbon, but hasn't made a bond yet. And the leaving group is starting to disappear from the carbon, but hasn't fully left yet. And so what we really have is a relatively high charge density right here. We have delta minus on both sides because the nucleophile was delta minus to begin with, and it's coming in and attacking, and the leaving group is delta minus and it's leaving. And so right here at the top of this pump, we have a delta plus and two delta minus. Carbon in between the two delta minuses, it currently lacks for electron density. It has less than it would like on both sides, and in the middle of this transition, it's relatively high in energy because it needs more electron density than it currently has. The nucleophile is starting to supply it, but hasn't succeeded yet. The leaving group is leaving, but hasn't entirely left yet. So this is a relatively high energy state. It's because of all the charges. So the presence of a polar solvent will be something that lowers the energy here. A dipolar solvent can get in and stabilize these charges a little bit. It can donate some electron density to the delta plus. It can put its delta pluses near the delta minuses and so on. So you're stabilizing that intermediate more than anything else. However, you don't want to do too good a job of stabilizing those intermediates because the starting material and the product both have a minus charge, usually on the nucleophile and the leaving group. So if your nucleophile is a delta minus and your solvent is too good at stabilizing this charge, then what the solvent will do is make sure that the nucleophile is no longer a good nucleophile. So we want the file to be polar aprotic because here are some of the classic polar aprotic solvents. So here are some of the classic SN2 type solvents. Really, acetone is a classic SN2 solvent, and the strongest SN2 solvents, if you really need an SN2 reaction to go, are really DMSO and DMF. Acetone is got a double bond to an oxygen, and you notice that that is a common feature both for dimethyl sulfoxide and dimethyl 4-mammin. In all cases, what you have is a relatively naked minus area in the molecule. This big strong dipole with a minus that's really exposed and a plus that's kind of buried. And what this means is that these solvents do an excellent job of solvating plus things like sodium ion, and they don't do nearly as good a job of solvating minus things. And so if you have a nucleophile that's floating around in a solvent like this, the plus is solvated really well. So like sodium of sodium methoxide, the plus will be surrounded by all these minuses. But the minus is naked. The minus is available to go ahead and make bonds. So polar aprotic solvents have this nucleophile as really exposed, ready to do an attack, but then these areas of delta minus can easily get in and solvate that delta plus. So more or less, polar aprotic solvents are the ones that stabilize the transition state relatively well. For completeness, I've illustrated a couple of weaker polar aprotic solvents like THF and ether. Usually these don't work all that well in actually running reactions in the lab because they're not polar enough. We tend to use these when we're trying to do SN2 reactions. These are solvents we use for other things. Polar aprotic means polar without protons that are easily used for acidic purposes. So for instance, methanol is a classic polar protic solvent. Water is the canonical polar protic solvent. Ethanol, polar protic solvents. Basically, all alcohols fall into the category of polar protic solvents. Why don't you want to use them when you're doing an SN2 type reaction? Well, really because they're too good at solvating things. Water, you know, is a solvent that's an excellent solvent for dissolving salts. Why? Because water can surround an anion really well and push all of the delta plus hydrogens toward that minus and really give a good solvation shell around that minus. Said another way, what polar protic solvents do is they lower the energy of the nucleophile by itself. They lower the energy of the leaving group too. So though they're lowering the transition state, they do a better job of lowering the starting materials, making it harder for an SN2 reaction to go. Again, the message is what you want is to minimize this distance between the starting material and the transition state. Polar aprotic solvents allow you to do that because polar aprotic solvents don't solubilize the nucleophile really well. They do a much better job of solubilizing the transition state, of interacting well with the transition state. Whereas the polar protic solvents, what they do is do too good a job of bringing down the energy of the nucleophile. And that means that this reaction then becomes harder because this gap, this energy gap, just got a little bit taller. So, if you're going to do an SN2 reaction, your solvent needs to be a polar aprotic one, acetone, DMSO, DMF. Those are your standard choices. These are somewhat acceptable choices, but more often than not, if you're trying to do an SN2, these are the three solvents you want to use.